that. No problem. Yeah, hello everyone, and yeah, thanks for the kind introduction. My name is Töebermann. I'm from the University of Applied Sciences in Lübeck in Germany, and I'm very happy to be here and give a talk about, well, this lengthy title will add a little bit different perspective because it's a grid perspective. The topic is part of a close research collaboration with the Fraunhofer IEE in Kassel, and it's part of a very large research project called Northern Germany Living Lab with 50 partners. The abbreviation is NRL, so the logo on the left side, and it's funded by the German government, so the logo on the other side. The topic is about grids and infrastructure, and the advantage, or in my opinion, to include it at least in some detail into energy system modeling, and of course, a little bit of how to do that. The topic is, well, a little bit special for this symposium, and some of the slides may go a lot into detail, but I will try to adjust it to the general takeaways. And last but not least, I'm just the presenter. The work was done by my team. Oh, that's missing on the slides. I'm sorry, Natalia, Kurt, and Gerrit. Well, the starting point is, of course, the energy transition. We want to have our future energy system to be 100% based on renewable energies. In Germany, we want to reach the goal in 2045. So just 20 years to go. And if you think about grid and infrastructure, well, you must plan these, what you have to do, well, now, if you want to have it in 20 years, at least for the times of the planning phase and the law in Germany. Another challenge is our system will be based most on PV and wind. We have already 50% renewables without just a few percent of hydrogen, but just 15% of the total energy system is based on renewables. So we have to do a lot within 20 years. So there are plans to install PV and wind in a massive way. And to handle that in the total energy system, well, there are a few options, of course. Sector coupling, we must electrify transportation, heating. We must integrate short-term storage and medium long-term storage, like batteries or maybe hydrogen, or using hydrogen in specific applications and sectors. And to enable all that, we have to do a lot about grid reinforcement and expansion. If you go to introduce hydrogen, well, more or less, then you have different amounts of grid reinforcement and expansion needs. So what is the best approach and the best pathway to end up with a working system in 2045? And of course, you can use flexibility. We heard something about that yesterday. And again, that helps for some parts of the grid development, but maybe it's not enough. So our research project is based on the idea that we want to learn how sector coupling with hydrogen really is achievable in the German structure, starting with hydrogen usage in transportation and industrial sectors, going around what is the effects on the national economy, the labor market, the needed qualifications, new business models, and also about networks and infrastructures and our system integration aspects. So, well, again, the topics, the challenges, and well, I focus on the grid reinforcement and expansion and the improved grid operation. we want to have a system simulation which allows us to enable to model the increase of PV and wind and hydrogen usage and all these things together with the needed grid development. So we know what the pathway for the future for the energy system, but also in detail what are the energy grids are doing and what are the limits of the energy grids do not allow to install. So starting point is, of course, a central view about what's happened during the pathway to 2045. And there are different scenarios of generation and consumption, which are regionalized to specific grid nodes in the model region. That is part of the Fraunhofer IEA, and there are a lot of assumptions in it, but it's a grid-free but consistent view of the future developments. In the middle row, you see the development of the onshore wind. Well, you don't see so much because in Schleswig-Holstein, the model region, we have already a lot of wind. On the left side is the North Sea, on the right side is the Baltic Sea, so it's a wind-intensive region, but there's still a significant increase in wind. You see much more in the increase of photovoltaics. Well, Germany is not the sunny state in the world, but still we rely heavily on that. And you see the development of the electrical vehicles, and there's a large dot in the south. Well, that's Hamburg, so Auckland plus something. So a lot of electrical vehicles are placed there. The rest is, well, more rural area. Also, that's just 3 examples, so a lot of more scenarios for development of bio gas production and other consumers, heat pumps, and so on. So these are also grid-free, just the usage and the generation of energy. So now we want to combine that with the grid perspective. So the starting point is we model the current grid. And in 2030, it may work with the existing grid. In 2045, the current grid is not enough anymore. So we do these simulation with the grid. We see the points where the grid is overloaded. And during the simulation, from time step to time step, we make an automatic grid reinforcement and expansion decisions, automatic grid operation decisions like switching or redispatch or use of flexibility, and also automatic placement of future assets like batteries or electrolyzers. And by this, we do not get only the path for the system, but also the implementation path for the needed grid reinforcements and expansions. And if you tweak a little bit about the decisions, if you want to go more to grid reinforcement or grid operation or placement of electrolyzers or batteries, then you end up with different results. And of course, the idea is to find the most economic and best solution. So what we do are really a lot of time-based grid calculations for each time step, a full time year series grid calculation, finding the overloads and doing something about the overloads until we solve the problems, including also placements of electrolyzers. Some small examples of preliminary results. You see in the top, there's a orange line in 2030, and it's just a yellow line or light orange line anymore in 2035. There's an increase in generation and consumption, so the orange line would be a red line, but due to the automatic grid reinforcement or placement action, this line is not overloaded anymore. Another example from just Lübeck, that's the grid, and the time series there shows the maximum load on all these lines. So they may be different from time to time. And well, you don't see so much, but Lübeck is a town, so usually it's much more consumption than generation. But in the increase from the first line to the last line with the loading is really based on generation. So additional solar power on the roofs. There's one peak in the February. There is the need for reinforcement should be obvious, at least from the grid operator view, but it doesn't change. That's something more about industrial processes. And last but not least, that grid and reinforcement decisions are more straightforward because that's just about the electrical grid. If you want to have to consider electrolyzers, then you have to look at both grids, the electrical grid and the hydrogen core grid, as it's called in Germany. And then you have to consider two grids together. So you have to simulate both grids and see if there's an overload in one grid and an overload on the other grid. Then it's maybe a good placement there. But you have to look at other details like what is the land usage in the surroundings of these overloaded areas and so on. So we set up a placement algorithm which use all these information to determine where the two grids are sufficiently close to each other so that a placement makes sense. Further narrow down the permissible areas based on where it is really useful to add something or allowed to add something like that. And then loop again with a lot of grid calculations over all these areas to check where these placements are useful. So just an example. And well, yes, to keep in time, the idea is give you just a brief overview of our project and the necessity to use grid calculations and grid simulations to cover the grid limits, which may not allow the ideas you have for your total system. And how to do it is, well, that's one of the ways to do it. It's a lot of grid simulation, a lot of time-based grid simulation. And if you learn more about that, would like to discuss that in more detail. So thank you very much. Yeah, well, that's it. Okay.
Thanks, Christian. Michael, are there any questions online? No. We might just move on to the next speaker, and people in the room can grab you at the lunch break. But thanks very much. It's great to have that perspective from Northern Germany.